in this lecture, what we're going to do is two things. We're going to discuss another kind of large cardinal called a Marlow cardinal. So this is, again, an inaccessible cardinal. So we can't prove that these cardinals exist in ZFC. Then when we finish that, that'll be the end of chapter 2. And we're going to move on to chapter 3, which is about formalizing syntax. And I'll say a little bit more about that when the moment comes. But first of all, let's have a look at Marlow cardinals. So I'm looking here at top of page 36 in the notes. It's definition 249. So a regular limit cardinal right? So that is already something called weakly inaccessible. It's called a weakly Marlow cardinal, kappa. So this is named after Powell Marlow, 2011. Remarkably early idea to start thinking about these kinds of properties at a very, very early stage in the development of set theory. So it's called Marlow in case the regulars below kappa form a stationary set. Below kappa. So recall stationary meant intersects every closed unbounded set. It's called strongly Marlow if it's both weakly Marlow and strongly inaccessible. So like inaccessibles, they come in two flavors, weakly and strongly. So if it is both weakly Marlow and strongly inaccessible. So in strongly inaccessible, recall means it's a regular limit cardinal, but it's closed under the power set operation. Any alpha less than kappa, 2 to the alpha is less than kappa. So the next lemma shows that the first weakly Marlow cardinal is not the first either weakly or strongly inaccessible cardinal. If kappa is weakly Marlow, then in fact it's the kappath weakly inaccessible cardinal. Right, so if here are the cardinals, here's kappa. There are already the order type of the inaccessibles below kappa is already kappa. So it's a fixed point in the enumeration of the weakly inaccessible cardinals. And in fact, the definition of Marlow says that the regulars must be stationary below kappa. And actually, what we'll see is the weakly inaccessibles are stationary below kappa. It just follows from the definition. And the class of weakly inaccessibles below kappa is stationary in kappa. So somehow the definition here is self-improving. After all, this could have been talking about just successor regulars, but actually it's talking about limit regulars. And if I cross out weakly and write strongly everywhere, the same holds. So the same is true for strongly replacing weakly. Or as I abbreviate it sometimes, W, throughout. Okay, so let's see why that's the case. So the idea of a Marlowe cardinal is that it's really quite far out. You've gone a long way through the inaccessible cardinals before you meet such a creature, if it exists at all. And in fact, it's not just a limit point of these weakly inaccessible cardinals, it's so far that actually the weakly inaccessibles below kappa are, semi-thick. This is what I was saying a stationary set is. It's like a semi-thick set. But actually the argument is quite simple. So as kappa is weakly Marlowe, the regulars are already stationary below kappa. Here. So this is a regular cardinal. The regulars are stationary below kappa. So actually kappa is already the kappath regular cardinal. But in any case, the regulars below kappa is unbounded in kappa, as in this picture. But now we look at the limit points here. Right, the closure of this class. Now these are not all going to be regular. For example, Aleph Omega is not regular, but Aleph Omega is in here. So this is the closure of here. But this is now closed and unbounded below kappa. Right, an earlier exercise said if you've got an unbounded class below a regular cardinal, its closure is CUB below kappa. By Marlowness, this is also stationary. Just by definition of what it is to be Marlow. This is stationary in kappa. But here's a CUB set and here's a stationary set. So in fact, the intersection of a CUB with a stationary set is stationary. This was exercise 213. But then what are these things in here, right? these are, everything in here is a regular limit cardinal. It's a regular limit of regulars. So everything in here is a regular limit of regulars. And that's what we call the weakly inaccessible. So the weakly inaccessibles are stationary in kappa. So the weakly inaccessibles are stationary in kappa. And replacing weakly by strongly throughout is just routine. Right? It really doesn't feature in the proof. So this does not affect matters. Okay, there's a kind of exercise I draw your attention to, which is kind of asking the same things kind of in the other direction. You could say, okay, maybe, okay, so you've convinced me, right, that the first, for example, the first weakly Marlow cardinal, kappa, is the kappath weakly inaccessible. Maybe the first weakly inaccessible cardinal, which is a limit of weakly inaccessibles, is Marlow. And the exercise says, no, the first Marlow is beyond that. So lambda is the least weakly inaccessible. That is itself a limit of inaccessibles. Okay, so then you can argue, using CUB sets, lambda is not weakly Marlow. And again, there's the same rider. You can replace weakly by strongly. Okay, now the exercise is quite short, but it does require an idea. Right? To show that something is not weakly Marlow, you'd need a CUB set in lambda, right, that avoids the weakly inaccessibles. So find a CUBC in lambda with C intersect weakly inaccessibles empty. Let me just informally write it like that. Okay, do get to be familiar with this definition of Marlow. It's going to come back to us later, and we're going to use them. So please spend time understanding what these Marlow cardinals will be. So formalizing semantics. This is an important part of Gödel's proof, because the idea is that we want to talk about definability, and definability is about meaning. For example, I mean, you may have, for example, a group, just to take a mathematical structure here. Here is a group, and there's a group operation and an inverse and an identity element. It's a field of its objects. So this is a mathematical structure. We might want to talk about what elements of a group satisfy a particular formula in the language of group theory. Right? So we might want to, for example, form a set of objects in here such that now something or other is true in the group. Some formula appropriate to group theory is true about these objects here when interpreted in the group. So this looks like something we already have, but actually we define this in our language outside the universe V, and we see what sets satisfy that. Likewise, we sit outside the group G here, and we look at the group and we see which elements satisfy this formula. Now, what we want to do is actually build up within set theory a subuniverse of V. So we want to build up within set theory a subuniverse of V. So the picture will be something like this. We have V here with the ordinals. And Gödel's construction of his constructible universe is a subuniverse of V. In general, it will look something like this. And this he called L. Okay. But the way the subuniverse is built up is by using this idea of definability. So just as we've got the V hierarchy, V alphas, V alpha plus ones, right? L alpha plus 1, instead of just being the power set of L alpha, which was how we'd get V alpha plus 1, we restrict that idea. We don't take all the subsets of L alpha, but just the ones we can define. So it'll be, just to abbreviate, things that are definable over this L alpha epsilon. Okay, not the power set of L alpha. We restrict it to just the things we can talk about. So we want to give this definition. We want to be able to give this definition and formulate it within set theory. So we need to define within set theory this definability. And talking about submodels or substructures of groups, subgroups, and so on, with reference to their language, this is called model theory. This is a branch of mathematical logic called model theory. If set theory is going to be able to formulate all branches of mathematics, we have to be able to mathematize model theory and these ideas of definability. And this is what we mean by defining within set theory semantics, because we have to say what it means for this formula about this group object to be true in this group. So we want to formulate this idea using set theory. So that's the task in hand. And the first thing that we'll do is go back to looking at absoluteness. So we saw ideas about absoluteness and how we could describe syntactically simple formulae, the delta zero formulae, as being absolute between a transitive class and V, or between two transitive classes. we want to go back and do some more work on absoluteness. And we're going to define, first of all, at the beginning of this chapter, the notion of a definite term and definite formula. So this will be an extension of delta zero formulae. And the idea is that a definite term and formula, this will capture for the most part what we need when we want to say that a transitive ZF minus model, particular formula is absolute between that and V. So we return to absoluteness. And there are, again, admittedly, a fair number of definitions here. So there's another sort of chunk of definitions about different kinds of classes of formulae. So the first thing we're going to do is of definite terms and formulae. Too many things beginning with the same letters. We've got define and definite here. We're going to define the idea of definite. So this is syntactic classification. Right? We just look at our terms and formulae and we say these are definite and these aren't. So it's just a division of our formulae into two types. And the idea, rather like delta zero formulae, is that you can, to an extent, locally determine what they mean. And we argue that definite terms and formulae are absolute for transitive ZF minus models. So this idea of restricting ourselves to looking at absoluteness for these particular classes is what definite terms and formulae are good for. So syntactic definition of what being definite is, and then we have this idea that the syntactic definition will cut out for us which are the absolute, cut out for us a class of concepts which will be absolute for when we look at transitive ZF minus models. Here, inside our universe V. And this idea of transitive ZF minus model, this will feature quite heavily now from now on. So it won't just be that this is transitive and delta zero formulae, extensionality and so on is absolute between W and V. We'll put more conditions on the closure conditions of W and we'll get more things absolute, right? And these are the kind of things that we want to use when we come to define this definability operator to give us the L hierarchy. Right? So that's the way it's going at the moment. So let's go straight then to definition 3.1 in the notes. So instead of me writing it all out by hand, let's look directly what's there. So we're defining the definite terms and formulae. So this is our syntactic definition for today. So we define them by induction on their complexity. I haven't formally given a definition of what the complexity of a formula or a term is, but you can imagine it's to deal with how many subformulae it's got and the tree structure which you use to build up a formula or for the formula for a defining term. So the simplest formulae are the atomics, and there at 1 you can see there's the equations x equals y, or x is a member of y, where x and y stand in for any of our official variables, vi and vj. If formulae phi and psi are definite, then so are these not phi and phi or psi, and then exists y, a member of x phi. So a bounded quantifier there in front of phi. So that clause 1 there already tells us that the delta 0 formulae are definite. Right? The delta 0 formulae were precisely those that were closed under negation, disjunction, and bounded quantification. So we're defining definite terms as well. So any variable x is a definite term. And if s and t are definite terms, so is, for example, the pair s and t. And so is s minus t, and so is the big union of s. So an alarm bell might go off at this point, because we've seen in the past that terms can define proper classes. I'm not allowed to say a proper class is a member of something else. But here he is saying that we've got this collection here with S and T members of it. So actually, this is a clue that what's coming is, in fact, that definite terms will always define sets and not proper classes. So over the page, I may have a definite term with some free variables in its definition. And I may have some other definite terms. So this says, if I substitute the definite terms in for the free variables, the whole thing is still a definite term. And likewise for formulae phi, if I substitute the definite terms t1 to tn for variables x1 to xn, so for those that are free in phi, this will result in a definite formula. So a definite formula is one with definite terms substitutable in it. So there's more substance here in the final clauses. If I've got a definite formula and some definite terms, then this declares two other kinds of things are definite. And they're a bit like separation axiom and a replacement axiom. This says, right, if I look at the members of y, I look at those x's in y which satisfy this definite formula, then this is a definite term, definite collection of things for us. And that is just separation. We're separating out from the set x, from the set y, those objects x which satisfy this definite formula. And here we're looking, think of t1 as being defining for us a function, perhaps. So there's a parameter x in there. But what this is the range of the function t1 on z. We're looking at all of those things, t1 of y's, for y and z. So I can think of this as like the range of t1. So it's like an axiom of replacement. This is giving us a definite term. So again, syntactic strings here, but that's how we're interpreting it. the term that defines omega counts as definite. And now a powerful clause. It's a recursion scheme. So it says, if I've got a definite term, which is a function, I can use that function to build up another function by recursion. And indeed, this will give us, we will declare that this function is definite as well. So here I am defining f by recursion. We assume we know what f is on the element z in y. And I define f of y. The x vectors, these are just parameters, other variables, other positions in the definition. And they don't dynamically feature in this recursion clause. So f of y is t, this function t applied to y, my parameters, and the set of things that I've already defined, the fz's for z in y. So assuming I know by epsilon recursion all the z's in y, what f of z is, this gives me f of y. So this is how we're going to build up definite terms, right? By recursion, by separation and replacement axioms, but only using definite data. So I'm just going to outline some of the features we have here. I'm not going to go through completely closely every aspect of the proofs you have here. It could be done, but it would just take too much time. And this is a case in point. In lemma 3.2, it says, in fact, the ZF minus axioms are enough to prove that if you've got a definite term defined as above, right, the term always gives you a set. Right? This was when I was warning us that we seem to be substituting indefinite terms inside sets. Well, we can do that because they will always be sets and not proper classes. And how we would do this is we would do this by an induction on the complexity of the term t. We'd say if I knew this result for simpler terms, I know it for a term t. So the main point here is that we don't use the axiom of power here when we actually define any of these terms here above. So definite terms always return sets. So that's the first thing that we should just, we can accept. Yeah. And now, as I said on the board earlier, we're going to be interested in terms and formulae that are absolute between transitive ZF minus models, M and N, say. So at the risk of some confusion, I'm going to call those terms and formulae absolutely definite. Right? They're absolute between transitive ZF minus models. And we'll abbreviate that as just AD. And this is always, if something is AD for a model, it will always be implicit that it's transitive and ZF minus model. And the idea will be that if something is, the definite terms are absolutely definite. Not necessarily conversely, right? But we can prove that the definite terms and the definite formulae in this theorem are absolutely definite. And that is that they are themselves absolute between transitive ZF minus models, MN. Okay, I will say a little bit about this. So how would we prove this? Well, we'd prove this. One way would be by simultaneous induction on the complexity of terms and formulae. So we've got a way of defining our terms and formulae in this theorem above. And that was essentially in terms of complexity. We defined definite for the simplest formulae and then how to get definiteness for more complicated formulae. We declared certain terms to be definite. And then we showed how we can use definite terms and formulae to define more complicated definite terms. So we've got an inductive process going on. I think of a formula as just being constructed by a little finite tree, right? We start with some atomics and we combine these up and we use disjunction and bounded quantification and we end up with a formula. And likewise, a term is a little finite tree. There are some basic things which we count as terms, such as omega and variables, and we build up the term, the defining formula of a term in the same way. So we would do this proof by induction on the construction clauses in that definition that was above. So there's one little point to be made. It's enough to show that definite terms and formulae are absolutely definite for a single ZF minus model between that and V. Because then if I wanted to show that a term was definite between an M and an N, I quote the result that it's absolute between M and V, and I quote it again to say that that's absolute between V and N. And that way I get it absolute between M and N. So what we show is that definite terms and formulae are absolute between transitive ZF minus models and V. V is also a transitive ZF minus model. So we take, okay, a given W, a transitive class term in which ZF minus holds. Now, we already know certain things, right? Atomic formulae are absolute for transitive classes, irrespective of what axioms are true there. Indeed, delta zero formulae are absolute, and that's mentioned down here at the bottom. So again, this here repeats what we had when we showed that delta zeros were absolute. Assuming that phi is absolute between W and V, let's look at exists X in Y, this bounded quantified phi. Well, officially, this means this, right? There exists an X, X in Y, and phi. This is relativized to W. Definition of relativization says this is a shorthand for there exists an X in W, such that this formula relativized holds. And I've already used the fact that X epsilon Y is equivalent to its relativization to W. So this is the only thing left that needs relativizing. So W is transitive. So to say there exists an X in W is just equivalent to saying there is an X when we're thinking about members of Y, because all members of Y are in W, because it's transitive. So I can get rid of that exists X in W, and I end up with this. If I know by induction phi is already absolute between W and V, I can just get rid of that superscript W. So knowing that it holds for W, I have that it holds for this bounded quantified formula here. So that justifies again, right, that delta zero formulae are going to be in our AD in this new wording. So the proof would then go through, looking through the various clauses as to how we build up terms and formulae and knocking them off one by one, saying, yes, that continues to validate absolute definiteness. So we go to clause 2, then clause 3, and clause 4, and we just check that this is what happens. We get what we want. And this is what's happening at the top of page 41 here. I suppose S and T are definite, and I show the things that I build at clause 2 out of S and T are definite. And this here repeats what we already saw in chapter 1, the relativization of big union of S to a transitive W is the big union of S. And I won't go through all of those steps again. Right? Likewise, if I've got that S and T are absolute, so I've got an S and T in W, then I've got the pair set in W. Again, because W is a model of axiom of pairing. And S minus T is similar. And for 3, this just goes through the moves that if I substitute things I know are definite into something I know is definite, I get something definite. And I won't go through all of these clauses here. Here I've got my T1 to Tn substituted into T0, and I look and see its interpretation in W. And for certain moves, I then see it's just the same as interpreted in V. So actually, right, to say a bit more, this equality is just a definition of relativization of the term, this long term here to W. And now we use here just the inductive hypothesis on the T1 up to Tn. And the next equality, I use the inductive hypothesis on T0. And the same thing would happen here for formulae. For 4, we've got these term building operations of separation and replacement. And we'd make the same kind of observations. I'd suppose that phi and T1 to Tn are definite. And here I am defining, separating out from Y elements X, which satisfy this formula phi. And I do this relativized to W. Well, if Y is in W, Y is a subset of W. So again, this is just the same as saying Y intersect W, intersect this lot here. Right? Here I relativize this term on the next line. And here I use my inductive hypothesis that I've already got some definite terms and formulae substituted in each other. And I already proved above that this is the same as this. And now I've left till here to use the fact that W is transitive, so Y is a subset of W. So this makes this have the same definition in W as in V. So that little separation scheme is absolute between W and V, only because the items going into it are definite. In general, separation would not be absolute. And I will skip over the replacement part here. I'd like to just linger a little bit here on omega. Omega was just declared by fiat to be a definite. Why is omega absolute between a transitive ZF minus model and V? Well, this isn't perhaps the shortest way of saying it, but it illustrates various other things. So we define omega as you start with the empty set and you close under the successor function. Well, let's say something about that, but also about ordinals in general. And the upshot here of A to F is that things on the left are being defined by using bounded quantification on the right. So actually, everything between A and F is defined by a delta zero formula. So being the empty set is just saying, for any element of X, you're not equal to yourself. Okay, so that fails for any Z. So X is empty. Here I've written X is transitive out using bounded quantifiers. Right. For any Y in X and for any Z in Y, Z is in X. So any Y in X is a subset. Being an ordinal is then delta zero. I've just written transitive as delta zero. And now here I've got a bounded thing that just says epsilon is a total order on any transitive set that's going to be an ordinal. So again, I can write that using bounded quantifiers. Being a limit ordinal, right, is again delta zero. I've established being an ordinal is delta zero, and if you're a limit, you want the empty set. And to be a limit means that for every element Y of U, there's a bigger Z. There's a Z in X where Y is less than Z. E just says that omega is the first limit ordinal. It's an ordinal, and sorry, a natural number is an ordinal, and it's not a limit ordinal, and it contains no limit ordinals. And to be omega is to be the first limit ordinal. You're an ordinal, you're a limit, but nothing earlier is a limit here. So being omega then is a delta zero expression, and so is absolute for W here. And what comes next is, I think, superfluous. It just shows that the successor operation, I could argue that the successor operation is absolute here. And lastly, just to finish up, again, I think just look at this quickly. We've got a function f, which is being defined by recursion. And we make the same kind of moves. T were given as definite. So interpretation of T in W is the same as in V. So we assume by epsilon induction that we've shown for any Z in Y that F interpreted on Z interpreted in W is the same F interpreted in Z, right? And gives us something in W. So now I'm going to make the same kind of moves. I'm going to say, let's look at the interpretation of F on Y in W. Here's its definition, its recursive clauses. I know that these gadgets in here, the F of Z's, are interpreted the same in W and in V. T does the same thing in W as in V. So T returns the right F for us. So recursions are involving definite terms and formulae are AD. Okay, fine. That will be enough for now. We will look further at these ideas again next time.